Okay, so loudspeaker now emits sound toward an air-water boundary, right? And then there's all this wavefront stuff. We'll deal with that in this part here. The first thing it says is the speed of sound is 340, and in water it's 1500, right? So this is, by the way, the slow medium. This is the fast medium. Let's call this medium 1. We'll call this medium 2. Okay, this is going to come in like this. And it's going to refract. And it says, what it says is, it says, determine the maximum angle. And by the way, this angle here is the same as this angle. Okay, so these are the wave fronts. Okay, this is the direction of travel of the sound. So this is compression, rarefaction, compression, rarefaction, compression. Okay, in that longitudinal wave. And then what they want to do is they want to find the critical angle, basically. What is the maximum angle? So we have to use, and this is in subtopic 4.4. We're going to use the Snell's law, but it's got velocities in it, right? So we've got n1 over n2 is sine theta 2 over sine theta 1. And then that equals v2 over v1, right? Now, if you cross multiply these first two terms here, you'll see that you get Snell's law, which is n1 sine theta 1 is n2 sine theta 2, which is all I'm used to, but anyway. But this is with velocities, so you can do this as well. In velocities, it comes out like this, right? So medium 1, our velocity 1 is going to be 340. Our velocity 2 is the fast one, so that's 1500 for water. And then they want you to find the critical angle. And remember, the trick there is to make the angle in the fast medium 90 degrees, which of course sine of 90 is just 1, okay? So ultimately this becomes 1 over sine theta max is equal to 1500 over 340, or isn't it just going to be the inverse sine of whatever it is that you can take an inverse sine of? In this case, 340 over 1500, because inverse sine you can't do it if it's bigger than 1, right? Okay. Anyway, you'll get an angle, and the angle is between 10 and 20 degrees, and it's much closer to 10. Okay. Then it says, draw lines on the diagram to complete the wave fronts. Okay. So for an angle that's less than that maximum angle, right? So it's going to come in at this angle, but this is a heck of a difference in velocity. So this is going to refract a lot. So let's draw like this guy going off like that, right? Ooh, that's a good straight line. Okay. Now these wave fronts, you don't have to draw one for C because C hasn't entered the water, but B and A are going to have wave fronts that start here and are perpendicular. See how these wave fronts are perpendicular to the direction of travel? Okay. You want to draw something that starts here but is perpendicular to this line. Okay. Your other clue, by the way, too, is that this wavelength gets bigger because it speeds up, right? So they get farther apart. It's like cars on the freeway, right? When the cars speed up, they get farther apart. But if you do that, if you draw a line here that's perpendicular to this, and you go ahead and use like a straight line or any kind of reference, you'll have little rulers, those clear rulers that I have on the test. But use that to draw wave fronts. They're going to look like this, right? They're going to be perpendicular to this. Only you have to start them there. I don't want to draw them for you because then I will have done all the thinking for you. Okay. All right. Enough of that one.